Hello everyone. So I will just discuss today about the single phase inverters. So let's see one by one. So this one is a half bridge inverter. Half bridge inverter means it is VDC by VDC is here and there is a split DC link VDC by 2 and VDC by 2. So when S1 is on, VDC by 2 is applied across VAB. So you get VAB equal to VDC by 2. When you apply, when you turn on S2, you get minus VDC by 2. That is VAB equal to minus VDC by 2. This is when S2 is on. This is when S1 is on. So these are the two states. If you now wish to draw the waveform, draw it like this. This is the pulse of S1. This is the pulse of S2. This is S1, this is S2, and your output voltage will be like this. That is plus VDC by 2 to minus, sorry, minus VDC by 2. So between these two voltage levels, it will oscillate, and if it is an RL load, current will be go like this. Let me draw this for you. This, then it will go like this, like this, like this. So this we have seen how the half bridge converter or the half bridge, rather than this, the half bridge inverter works. Now let us discuss its waveform that we have that we just saw, that the waveforms look like this. Now we will see the full bridge inverter. So this is the full bridge inverter. So as the name suggests, you can see that there it's a full it's the bridge is full with four devices, that is S1, S2, S3 and S4. So it's clear with this that the S1, S2 and S3, S4, these are the four devices here. And if you draw the voltage waveform, it will look like this. That before the drawing the voltage waveform, let me just write down the table for you, that S1, S2, S3, S4. uh, S1 and S2 are always complementary. That means if S1 is 1, S2 needs to be 0. If S2 is 0, S1 is 1. And for S3, S3 and S4, they are also complementary. That means when S3 is 1, S4 is 0. When S3 is 0, S4 is 1. So this is called complementary switching. Now let me take only two switches, that is S1 and S3. S1 and S3. So when S1 is on, you can see that VAO is like this. This is VAO. So this is the plus, this is minus. So what is the value of VAO when S1 and S3? Okay, let's only take AO, and let's take BO as well. So when S1 is on, VAO is how much? A to O is VDC, right? When S1 is on, it is VDC. And if S3 is also on, then what is the value of VBO? If you look at VBO, it will go like this, right? So value of VBO is also VDC, right? For S1 and S3. So what is the total value of voltage? VAB is 0. Now if S1 is 0, let me draw this for you. If S1 is 0, that means this term, this is that means S2 is on, right? If S1 is 0, S2 is on. So S2 is on means S2 is short circuited like this from this point to this point. Is that clear? From this point to this point it is short circuit like this. So if this is short circuit, you can say that the VAO value is VDC. No, sorry, VAO is going to be 0 and S3 is 0 means S4 is 1, right? You can see that S4 is 1. If S3 is 0, S4 is 1 like this. You can see here S4 is 1. So when S4 is 1, that means S4 is on. Okay, S4 is on. So B2O is also short circuited. So this is also 0. So VAB is again, VAB is nothing but you know that if I need to actually write it like this, that VAO minus VBO. Okay, let me write it here. Is VAO minus VBO. So this also is 0, right? Now if is S1 is 1 and S3 is 0, that then we will get this is VDC and this is 0. So we will get positive voltage level plus VDC, and if S1 and S3 is 0 1, then we will get what? This will be 0 and this will be VDC, so we will get minus VDC. So by this we can get 4 voltage levels, 0 0 plus VDC minus VDC. Now let me show you some waveforms. So the waveforms are shown here. So you can see that when the gate pulses are, this is S1, this is S2 complementary, this is S3 and this is S4. You can see that this is VAO, this is VBO, and VAO minus VBO you go get VAB, which is varying from plus 100 to minus 100. So this is straightforward. Now let me go back to the current. Let's say there is some RL load is there. So let's say this is an RL load. So RL load means this is let's say this is R, and from here to here there is some L. So let's say this kind of load is there. Instead of this part, this is RL load. So the current will be like this. When you are applying plus 100 it will rise, and when you are applying minus 100 it will fall. So it will rise and fall like this. So this will happen like this, and the source current will be, you just look at, if your S1, so if you need to find out the source current, you have to apply the KCL here. So the current through switch S1 is IS1 and current through switch S3 is IS3. So IDC equal to nothing but IS1 plus IS3. So in this duration, which switches are on? If plus 100 you are applying, that means S1 and S4 are on. So in this duration S1 and S4 is on, and in this duration your minus 100, that means S2 and S3 are on. So in this duration S2 and S3 are on. So you can see that the direction, so current 3S1 IS1 will be the AC side current, load current will be the IS1 current. So it perfectly replicates whatever the source current as the DC side current. However, in the next half cycle you can see that the current through S2 is this one, right? The negative current. Let me highlight this properly, that this one is this negative current. However, let me see the direction of this current, because I have considered my load current in this direction, right? This is my load current direction, and IS3 direction I have taken in this manner. Now if you see that if I have to consider the load current in this direction, if it is like this, that means it is flowing like this, then the current goes on this side, right? So the current must be the opposite of the direction of IS3, right? So the load current's direction is opposite the direction of the IS3. That's why what we have to do, we have to reverse this. So whatever we are getting here in this case, this part we have to reverse here. So we have reversed it. So this is becoming my DC side current. So this is the concept of AC side current and DC side current explained here. Now let me take the example of a quasi square wave. That means I have given a phase difference. So between the pulses there is a phase difference like this. So you can see there is a phi. So from here to here also there is a phi. So previously what was happening, you see that the gate pulses were perfectly synchronized. That means from here to here these are perfectly synchronized, you can see. Okay, here let me see the gate pulses. So this is S1, this is S2, S3 and S4. So S1 to S3 you can see they are perfectly synchronized. So in this case S3 is basically complementary of S1, right? Sorry, let me write it properly. So S3, if you consider it as a variable gate pulse, so it is complementary of S1, right? S1, S2 as you see here, and S3 and S1 as you see here, they are perfectly complementary. Now in this case, what I have drawn, only S1 and S3. Okay. So this is the gate pulse of S1 and this is the gate pulse of S3, which is also, by the way, is the pole voltage. Okay, so pole voltage of the system means VAO and VBO. So this is my, let me write it down here. This is VAO and this is VBO. So you see, previously we saw in this case that whenever you are giving, you are checking at VAO. Okay, whenever you see S1 is 1, you are getting VDC, right? Whenever S1 is 0, you are getting 0. And you see for VBO, okay, let me just highlight. This is yellow, this is also yellow, so they are corresponding to each other. Similarly, this S3 is related to VBO. Okay, so if you see when S1 is on, okay, VBO is VDC, 0 means it is 0. So we can easily write VAO equal to S1 into VDC and VBO equal to S3 into VDC, right? So whatever the voltage waveform of S1 and S3, it will perfectly replicate that. So if your if your S1 and let's say your S1 waveform is like this. Okay, let's say this is your S1. You can easily say, let's say S1 is changing from 0 to 1. This is our waves we have defined. Now your VAO will be changing from 0 to 400, 0 to plus 400 volt. Or you can say if this is VDC, so this will be 0 to VDC. The waveform will be perfectly same, just instead of 0 to 1 it will be 0 to VDC. So that is the only change that will be there. So they are following the same waveform. Now if you apply a phase shift between S1 and S3, the same waveform repeats. VAO and VBO also has a phase shift phi like this. So you can see that for this period phi, or there is an overlap period phi. Okay, so what happens in this period? Let's analyze this. What happens in this period? So in this period we can see that S1 and S3, in this case they are both 0 and 0, right? They are both 0 and 0. However, if you see in this case they are both 1 and 1, right? So at one case they are both 0 0 and another case they are both 1 1, right? Is this clear to you? Let me take a little bit uh, uh, another bit smaller. So here it is 0 0, here it is 1 1, right? These are the two durations. So during 0 0, what is the output voltage? We have already seen. During 0 0 output voltage is 0, and during 1 1 also output voltage is 0, because VAO equal to VBO in this period, and you can see that the VAO is actually equal to same. They are both same. Yeah, they are both 0, and here you can see they are both plus 100 or whatever. So now you see the waveform changes like this. So this is we call a quasi square waveform. Okay, this is the quasi square wave. Now in this quasi square wave, this is the AC side current. If we look at the quasi square wave, the AC side current will now be like this. Okay, and DC side current, it will be like this. During the zero period, what will happen? The DC side current will be zero, because during the zero period, what is happening when S1 and S3 are both either turned on or turned off? What happens that the load current completely freewheels in the top path. Okay, this is how the load current will freewheel, or the load current may also freewheel at the bottom path. Okay, so when the load current freewheels, it does not go to the source, right? It is free wheel among these switches. So therefore, this current is zero during this period. Okay. So if we increase the phase shift further, let's say I have increased, so you see that this duration has reduced now, right? This duration has reduced. Now as this duration is reduced, you can see that the waveform has that impact here, that the impact of reduction, and the DC side current, as you can see, is going increasing like this, increasing like this. Okay, and in this period DC side current actually is zero. This we have already explained why this becomes zero, because it freewheels through the inductor, through the MOSFET switches. Okay. Now if we see the phase voltage FFT of both of them, we can very clearly see that this is let me first write down which one is what. So this is square wave, and this is quasi square wave. Okay, so in square wave the waveform is like this, right? In quasi square wave the waveform is like this. So these are the two different cases for quasi square wave and quasi square wave. So in square wave, the voltage FFT, if you look at it, or the phase current FFT, you can see that the magnitude is quite high, right? But if you see the phase voltage FFT in the quasi square wave, it is very small, right? It is very small. So when we, not very small, but it is reducing. So definitely square wave to quasi square wave, when you go, it is becoming more sinusoidal in nature, because unwanted harmonics are reducing. So let's say you have a sine wave. Okay, and there are two ways of representing it. One is square wave, another is quasi square wave. So this one is better for you, because it has less unwanted harmonics. Okay, now our target is to perfectly emulate the proper sine wave, which is this one, right? I want a method where this will be a perfect sine wave. Okay, no, not a square wave or anything. So to do this, what we will know, that we have to use PWM techniques. Okay, so now we will see the method of pulse width modulation. So first, to understand pulse width modulation, first let us see the example of a buck converter. Okay, so we'll start with a buck converter, then we'll come to the pulse width modulation. So here only we will see how from buck converter we can come to the pulse width modulation. So in buck converter, Let's say this is a standard buck converter like this. So actually this switch is nothing but a diode, but let's also represent it like a switch. Then there is L, C and R, right? So let me consider this as the load, okay? Let me consider this as the whole as the load, okay? Now this is my point A, this is O, this is VDC. Now if you look at it, the output voltage, which is VAO, is always D into VDC, right? D into VDC. Now if you apply in VAO is a perfect square wave, right? Now this LC or only the L also has a low pass filter effect. Now what happens that it eliminates all the unwanted harmonics from here and it makes it a proper sinusoidal DC. No, sorry, proper DC it makes it. So this is my V output, which is nothing but DC. So you already know how to actually eliminate these harmonics and to make it proper DC. Now let's say if I change this duty cycle, now in this duty cycle D is completely fixed, right? But if I make this, let's say sinusoidal, let's say the duty cycle itself is sinusoidal like this. So instead a proper DC, I make it sinusoidal like this. Then what will happen? That this VO is also expected to move in sinusoidally, right? So this is the fundamental of a pulse width modulation, that I just change this D or the duty cycle in a sinusoidal manner, and this way I can also create a voltage which is sinusoidal in nature. Now instead of calling it simple duty cycle, we call it a modulation wave or the modulation signal. And modulation signal MA equal to modulation signal, let's say uh, M equal to MA sin omega t. Okay. So this is my modulation signal. I have to apply it like this. Now how to actually generate the gate pulses? Now you already know that, or let's take a triangular signal. Now if you take a triangular signal like this, okay, and if you compare it with a DC, what happens that below it, if you draw, let's say this is my uh, TRI triangular, and this is my modulation signal. So M, let's say S, modulation signal TRI and MS. So if write it using this, TRI greater than MS, if TRI greater than MS, S1 equal to 0, otherwise, sorry, if it is greater than, then S1 equal to 1, otherwise S1 equal to 0, right? If I do this, then how my modulation will come, let me show you. So in this duration, T1 is a triangle is greater than MS, right? In this duration, TRI is greater than, so duration it is 1, and in this duration my TRI is less than, right? In this duration it is less, so what we will do in this duration, it will be 0 again, right? And if I take a complementary of it, it will be like this. Okay, so this is how the PWM works. Let me show you a very good waveform of it, which is here. So you can see that in this duration, uh, my triangle, in this duration triangle is higher, so this switch is 1, which is S1, and sorry, this is S2, okay, and this is S3 and S4. So S1 and S2, S2 is complementary of it, S3 is again identical to S2, S2 and S3 I have taken it identical, and S1 and S4 I have also taken identical, okay. So this is how I can use PWM here. So this is my S1, this is S2, this is S3 and S4. So if I have to actually show you this PWM, or show you the generation of this PWM, or a block diagram, in block diagram sense how it will look like is this way. So this is my triangle, which is nothing but this kind of waveform. This is modulation signal, which is like this. Now this is a comparison block, comparison block, okay. And I am getting all the pulses here, as you can see that S1 and S3 S4 are identical, they have the same pulse. And when I do a knot, I am getting S2 and S3, they are also identical, okay. So S1 S4 S3 S2 S3 are identical. So now when I compare them here, so you can see this is my get pulse S1 S2, and there are my gate pulses S3, and this is S4, okay. And this is my triangle, this is my triangle, and this is my modulation signal, mod, okay. Also triangular signal is called carrier, okay, carrier signal, triangular carrier, okay. Now you know that gate pulses S1 and S2, when I have shown the out VAO is identical to S1, and VBO is identical to S3, okay. Now I subtract here VAO minus VBO. Now if I apply it to an RL load, if this voltage, whatever I got here VAB, if I apply it to an RL load, I will get this kind of current. So you see that the current has lot of improvement. Forget about the DC side current, it's beyond the scope of our current discussion, okay. Just concentrate on the AC side current. So this is how the AC side current will look like, okay. Is that clear to us? I think so, okay. Now to this much I would like to show you a simulation here now, and in simulation we will see that how this is implemented and how this looks like, or the waveforms how it looks like. So we have used Plex based simulation. So Plex is a very nice software for simulation, and we are using it in our study. So uh, this is S1, S2, S3 and S4, as you can see. Okay. Now let me show you the PWM. PWM is like this. Okay, let me uncomment it. Currently it is commented. So now I have it uncommented. So this is my PWM block diagram. So this is 1000, means this is the value of the carrier frequency, and this block is convert it to a triangular waveform. Now let us see how it is, okay. So we got the triangular waveform, right? So 1 to -1 it is varying, right? It's clear. Now let us see the modulation signal. Modulation signal also we can see that it is varying from 1 to -1, right? Now if we see them together, it will look like this. You can see that 1 and -1 is varying like this. So now 1 and -1 means the triangle carrier and the modulation wave are varying from 1 and -1. And if we see the get pulses, let us zoom in this plot. Okay, so first let me just show you how S1 looks like. See, let us zoom only here. So in this case, until this point, can you see that this period is completely triangle has higher value than the modulation. Red is the modulation, right? Modulation signal. So triangle is higher. So in this period, you can see it has higher value. Means higher value means it is stayed high. Okay. Now in this duration, you can see that it has low state. Why this is low state? Because triangle is lower than the modulation. Okay, and similar pattern follows in the whole duration. You can see that here it is quite high and it goes to minimum, then it slowly pulse width changes and it goes to maximum. So you can see that the pulse width, if I see of a whole actually signal, it changes kind of sinusoidally, right? It is changing sinusoidally. Let me show you one thing here. I can use this software. Where is this? Please wait. I will use this G ink. Okay. See, so you can see that in this case the get pulse is changing sinusoidally, right? Get pulse is changing sinusoidally, means the pulse width. Pulse width minimum here, pulse width is maximum here. Okay. Now let me introduce another pulse. This is which is this one. I'm sorry, one second. So, this is okay, perfect. Now let me show you S1 and S2 together. Okay. Now this is S1 and S2, right? Let me include S3 and S4 also. So this is S3 and S4. See all the switches pulses you can see, right? S1, S2, S3, S4. So let me now show you the output waveform. Output waveform can be observed here. Mm, one second. Okay. See, this is the output waveform. Okay, let me remove the DC side current from the plot. So as you can see that my output voltage is like this. Output voltage is this one. Okay, it is changing like this. So this is maximum and this is minimum. Now if I have to, one second. Now if I have to actually draw, you can see that the pulse width is changing like this, right? Pulse width is minimum here, right? This is the pattern of the pulse width. See, now in this case it becomes maximum, right? Then again it becomes minimum. So if I draw the average pulse width for this phase voltage, you can see it also follows a sinusoidal manner, in a sinusoidal pattern. So this is the reason why we call this pulse width modulation, and it is sinusoidal pulse width modulation because the pulse width is changing in sinusoidal manner. Now let us see how we can improve the phase current further. So this is nearly sinusoidal, as you can see. Okay, nicely it is sinusoidal. But how can we make it even more sinusoidal? Okay, there is still some ripple here, right? You can see that some ripple is here. So let us try and improve this. So the one thing we can do is we can change the switching frequency to 5000. Okay, if we change the switching frequency, see, it has nicely improved, right? It has nicely improved, you can see. Now let's say we keep the switching frequency same 1000 only, then it again becomes bad, right? Okay, let me simulate for 0.0. The two cycles I'll simulate. Okay, see, it's not that good. Now what we can do is we can change this inductance value to, let's say, 0.1. When you change to 0.1, now you see it improves, right? Let me simulate it for 1 second. See, it is quite nice, right? So either we can increase the filter, that is this inductance, or what we can do, we can change the switching frequency, which can keep 5000. Okay, so these are the methods. Now there is another thing also we can do, which we will learn here. That is 1000, right? Let's keep it 1000. Okay, and we can see that this is bad. Okay, so instead of bipolar we will use unipolar PWM. So why we are actually saying that this is unipolar? Because you see that sorry, we are saying is bipolar because you see that at any given switching period the voltage is fluctuating from 100 to -100. So these are the two poles, right? Plus 100 and minus 100. So between these two polarities the voltage oscillates, so that's why we call it bipolar PWM. Now what we can do, we can make it unipolar. That means we will click on this and we uncomment and we will use this. Now now you see it has improved so much. Okay, the current waveform is very much good, right? See, current waveform is so good. Why this is happening is, now you see that we are using unipolar. That means now the voltage is fluctuating from 0 to 100. At any given period, there is only one pole it will go. That is 100. To 0 to 100 it will go, or it will go from 0 to -100. So that's why it is called unipolar PWM, because at only at one polarity it will go from 0. Okay. So either it will be 100 or -100. So this is how we implement, this is how by unipolar PWM works. Okay, now how we are implementing unipolar PWM? So what do? We take this modulation signal and we take actually a negative sign, that means -1 of it. So we take like this and we take both the sine waves. So one sine wave goes like this, another sine wave at the bottom, completely phase opposite. Okay, and the first sine wave or the red sine wave only provide pulses to one leg, that is S1 and S2. Okay, so S1 S2 corresponds to the red one. Okay, let me just show you this by deleting the blue one. So you can see that this is perfectly matching, right? These things are perfectly matching, these crossings. So you see that this crossing is perfectly matching. Now at this point, if you see the blue sine wave, it does not have any impact on these two pulses, right? S1 and S3. Sorry, this is S1 and S2. Now this green one or the blue one impacts S2, sorry, S3 and S4, which are these one. Now see, now the blue one is crossing here, right? So you see S3 and S4 is impacted by the blue one, or the of which is phase opposite sine wave in this case. Okay, so now you see, now let me remove this one also. So here you see it is impacted by this, right? Now I can show you anywhere else also. Now here you see they're being impacted, right, from the blue one, not from the red one. See, the red one has no impact on these pulses. So if I have to tell you, then I would say that this blue one impacts these pulses, that is S3 and S4, right? The blue one impacts like this. And if I see the red one impacts S1 and S2, which are these two pulses. Okay, so this is how we do it. So you know that this is for the this half of the inverter, right? And this is the second half of the inverter, that is this side leg. So these are the two legs which are being impacted. Now if you see the bottom leg or the side leg, this leg has no impact, and here this leg has no impact. Okay, these are not being supplied. So these pulses are for these two switches, and these the bottom pulses, that is S3 and S4, are for these two switches. So this is how the uh, unipolar PWM operates. Okay, now let me show you it's okay, we have already seen it like this. Now let me go back to the simulation, and in simulation we will show you how the current waveform looks like. As you can see that current waveform is really nice, and current waveform is has lots of improvement over the bipolar PWM. Okay, now let us go back to our presentation. Okay, we will present again. One second. Okay, we have started the presentation. Okay, so we have just now seen that how bipolar PWM works. So you need one sine wave and completely a phase opposite version of sine wave, right? So this sine wave is for if you have these four switches like this sine wave will supply one of the gate, one of the leg, and this pair of sine wave will supply the another leg. This is how we do it. Okay, the unipolar PWM. Now unipolar PWM output also we have seen until this much. So unipolar and bipolar, if we have to compare, let me just compare that. Unipolar PWM is better than bipolar PWM in terms of harmonics. Okay, however if you try to actually compare the harmonics count, okay, harmonics count is always actually less in unipolar PWM. Okay, that's why it is better. So we will conclude our discussion at this point, unipolar and bipolar, but we will revisit a few part of anti-parallel diode operation and other things little bit more in the next part. That is, let's say you have a inverter leg which is like this. Okay, and you have an anti-parallel diode here. Okay, so this part is a MOSFET. Okay, Now let's say you have a current source connected here. Somehow some current source is going here like this. Okay, so you know that gate pulses needs to be completely complementary here. That means it will be like this. Now if you zoom into in this direction in practice, what will happen, that one pulse will fall like this and another pulse will rise like this. Okay, so there will be an overlap. Okay, so for a brief amount of time, if this is, let's say, S1 and this is S2, so S1 and S2 will both be turned on, okay, and what will happen, there will be shoot through. This is called shoot through. So in this time, if you, let's say, you have turned off both of the switches, that means you give a dead band, means there will be some period when you do not actually turn on the switch. So in this period it will be dead. Okay, so let it fall first, you wait for some time, then you start it. So this period is called dead band. Okay, and what happens during this time? Okay, if the current was flowing in this direction, it will flow through this anti-parallel diode. Okay, the top one anti-parallel diode, and the vice versa, if the current was flowing at that time the opposite direction, that means in this direction, then the current will take the bottom anti-parallel diode. Okay, so this is how anti-parallel diode helps in the operation of an inverter.